Once we understand function notation, then we can use it to combine functions in different ways. In this video, we'll study arithmetic operations on functions. Now, that may sound a little bit strange, but this word right here, when used as a noun, we pronounce arithmetic. But if it's used as an adjective, as it is in this case, we pronounce it arithmetic. So we're looking at arithmetic operations on functions. That is, we're going to learn how to add, subtract, multiply, and divide functions. Suppose f of x and g of x are two functions. Define the four basic arithmetic operations as follows. First of all, we'll define the sum as f plus g of x. These two functions share the same argument, so we're going to separate them into two individual functions. So the sum, f plus g of x, represents the sum f of x plus g of x. Really, the key to understanding operations on functions is deciphering the notation. Let's take a look at the difference. We have f minus g of x, which represents the difference, f of x minus g of x. Now, when we're finding the difference of two functions, if g of x happens to have more than one term, then we will need to enclose g of x in a set of parentheses. The product can be expressed concisely as f times g of x, and when we expand that, it represents f of x times g of x. Again, when we're dealing with a product, if f or g contain more than one term, we'll want to enclose those also in a set of parentheses. And our last operation here is the quotient, f divided by g of x. We can expand that as f of x divided by g of x. Now, that quotient will only work provided that denominator is not equal to 0. So the first step in evaluating an operation on a function is to take it from the concise notation on the left to the expanded notation on the right. And then that expanded notation is basically a set of instructions for how to execute the problem. Let's give this a try on example 7. We're going to begin with two functions. F of x equals x squared plus 3, a quadratic function, and g of x equals negative 2x plus 4, a linear function. Find each of the following. First, we want to evaluate f plus g of 1. So we're working on a sum, and notice our argument is equal to 1. So we're going to expand this into the two individual functions. That is, we want to evaluate f of 1 and add it to g of 1. Now, if we look at the notation f of 1, it's a set of encoded instructions. It's pointing us to the function called f of x. So to evaluate f of 1, we're going to be using this function rule, and our argument is 1. That is, we're going to plug 1 in for x. That gives us 1 squared plus 3. That completes f of 1. Then we're going to add it to g of 1. Now, g of 1 points us to the function called g, which means this time we're going to be using this function rule, but our argument is the same. That is, we're going to plug in 1 for x. So I'm going to use a set of parentheses around that negative 2 to separate it from the plus on the left. So we have negative 2 times 1 plus 4. Previously, we learned how to evaluate functions. Now we're just evaluating two functions in one problem. Once we have everything plugged in, then we can execute the arithmetic, remembering always to follow the order of operations. So 1 squared, of course, is 1. Let's work on our multiplication next. Negative 2 times 1 is negative 2, and then plus 4. So 1 plus 3 is 4, minus 2 is 2, plus 4 gives us 6. So f plus g of 1 is equal to 6. On example B, we have the quotient f divided by g of 0. The first step is to expand this condensed notation into the more expanded form. That is, each function is going to receive that argument 0. So we're going to execute f of 0 divided by g of 0. Now, on the top, we have f of 0. F is pointing us to the function called f of x. So we're going to be using that function rule x squared plus 3 again. But this time we're plugging in the argument 0. So we end up with 0 squared plus 3. In the denominator, we have g of 0. G is pointing us to that second function, negative 2x plus 4. That's going to be the rule that we use, and we're going to plug in x equals 0. So we end up with negative 2 times 0 plus 4. Now before we go any further, working with the quotient, you may have remembered our stipulation up here. The quotient only works provided g of x is not equal to 0. And here on example 7b, we're plugging in 0. So there's a little bit of a difference between the stipulation and what we're doing here. So to understand this, let's continue a little bit further here on example b. So in the top, we have 0 squared, which is 0, plus 3. That's going to give us 3. And in the bottom, we have negative 2 times 0, which is 0, and 0 plus 4 is 4. Notice the output of our denominator is non-zero. We got 4 in the denominator. We didn't get 0. So back up here to this stipulation, this is not saying that we can't plug in a 0. We can't get out a 0. That is, if the value of the denominator, when I plug in the argument, is equal to 0, we'll have an undefined operation. So what we've done here on example B is perfectly legal. We plugged in a 0, and we have a non-zero denominator, therefore the operation is defined. Let's try f divided by g of 2. So we're going to execute f of 2 divided by g of 2. So in the top, we're going to use the function rule that goes with f. Remember, that was x squared plus 3. Replacing x with 2, we have 2 squared plus 3 in the top. In the denominator, we need to evaluate g of 2. And remember, g was negative 2x plus 4. Our argument in this case is 2. So replacing x with 2, we have negative 2 times 2 plus 4. Let's follow the order of operations. Executing exponents first in the numerator, we have 4 plus 3. Multiplication in the denominator, negative 2 times 2 gives us negative 4 plus 4. Now notice what happens this time. The numerator is equal to 7, but the value of the denominator is 0. That's the problem that we want to avoid. When we get a 0 in the denominator, our operation is undefined. So we plugged in a 2, but we got out a 0. So we would say f divided by g of 2 is an undefined operation. Now that we're warmed up a little bit with a couple of these operations, let's change the problem just a little bit. We'll change it in 2 ways. On example 8, we have 2 new functions. So f of x is the quadratic function negative x squared plus x, and g of x is the new linear function 4x plus 2. What's different about these problems, notice our argument is not a number this time, but a variable. So we're going to plug in a variable, essentially creating a new function. So let's execute f minus g of x. I'm going to expand this into the 2 individual functions, f of x minus g of x. Now, we're going to replace f of x this time with its entire function rule. So notice f of x is pointing me to this function. Because of this equals here, this function rule is equivalent to f of x. So they're interchangeable, right? So I'm going to completely replace this f of x with its function rule, which is going to look like negative x squared plus x. Remember, f of x does not mean f times x. So I'm not multiplying anything by x here. I'm just replacing the function name with its equivalent function rule. Okay, that takes care of f of x. Let's copy down the minus in between our 2 functions. And now we're going to do the same with g of x, except we're going to replace g of x with this function rule, 4x plus 2. Now, we have everything plugged in here, but I have a mistake in this problem. Can you detect what it is? Something is missing. Well, we're attempting to subtract all of g of x, and the way I have it written now, I've just subtracted the first term of g of x. In order to subtract the entire function, we need to enclose it in a set of parentheses. Then we're actually subtracting the entire function. This means that we're going to have to distribute the negative on the next term. And when we do that, we will have subtracted both terms of g of x. So be really careful about that when you're finding the difference between 2 functions. Make sure you put that second function in a set of parentheses. So distributing the negative, we get negative 4x minus 2 on the end, and then we're going to combine like terms. So we have negative x squared minus 3x minus 2. And by the way, that's it. That is where we stop. You may be tempted to, set it equal to 0, factor it and solve it, because we're kind of in that equation solving mood from the last unit. But here our goal is to plug in the argument, simplify, and that's where we stop. So if you plug in an argument that's a variable as opposed to a number, you're going to get out a variable expression. If you plug in a number like we did previously, if you plug in a number, you're going to get out a number. So plugging in a variable is going to give you a variable expression. Okay, using the same two functions, let's work on a product. We want to evaluate f times g of x. Remember, this condensed notation means we're multiplying the function f of x times the function g of x. Now let's be a little more proactive on this problem than the previous one and recognize both f and g have more than one term, so it's going to be necessary for us to keep those rules together in a set of parentheses. So as we did on the previous problem, we're going to replace f of x with its function rule, negative x squared plus x, and we're going to replace g of x with its function rule, which is 4x plus 2. Now that we've plugged in the function rules, we're going to execute the operation, which in this case is multiplication. Because we're multiplying two binomials here, we can use the process of FOIL. So the product of our first two terms, negative x squared times 4x, gives us negative 4x cubed. The product of our outside terms would be negative 2x squared. Inside terms give us a product of 4x squared. And last, we have plus 2x. Let's be sure and simplify by combining those middle terms. Negative 4x cubed plus 2x squared plus 2x. Now, our goal here is just to execute the operation. Remember, we're not solving for anything. So we plug in our argument, in this case a variable, we simplify, and that's where we stop. So that is arithmetic operations on functions. Adding, subtracting, multiplying, and dividing. The key is to learn the notation. Go from the condensed form into the expanded form, and then substitute and simplify.